Good morning, Dr. Carney. For my name reaction video project, I did the alder-ene reaction, and it's similar in a lot of ways to the Diels-Alder reaction we discussed earlier in the semester. And so for the general mechanism here, you have your enophile and a general ene. Electrons from the double bond then kick out the electrons in this alkene, causing electrons from the carbonyl to go back up on the oxygen, and then in the intermediate, the electrons come back down to reform the carbonyl, and the electrons in this double bond grab a hydrogen to give you a cyclic shaped product almost. For the reaction energy diagram, it's exothermic, as you can see by your total change in enthalpy here. And both the ene and the enophile have a higher energy than your actual alkene product, with the intermediate, or the transition state being much higher in energy. For my application, like a research article, I looked into the pharmaceutical application of it, and basically the gist of it was that this reaction is basically being used to synthesize new MS medication, and it's 3,4-disubstituted chromium, and it's turned out to be a much more efficient and economically friendly option for both the producer and the consumer. But they're still looking into other ways and may be applicable to new medications. For the IR spectrum here, I have both the reactants and products are very similar in that they both show a single alkane bond here, which is a strong peak here, and then a carbon-carbon double bond, which is here. And they both have the same bonds essentially in both the reactants and the products. So it's just a matter of what's actually formed. And then for my carbon environments here, it's pretty similar in that they both have 4 total carbon environments, and as you can see here, there's no differentiation between the types of carbon environments, so it's hard to decipher between the reactants and the products, just in that you can isolate the product compared to the 2 reactants you start with, but they're both alkenes. And it was similar in that the hydrogen NMR, the only difference in the hydrogen NMR is here you have this sextet because it forms in the cyclical shape, where you have 2 hydrogens here, but you have a single hydrogen coming off here at a double bond, and 2 more carbons coming off here. Excuse me, that would be a quartet that you can see here. And so ways to speed up the reaction I found were primarily by increasing like a Lewis acid catalyst, because that drives the faster equilibrium rate between the alkene and the enophile due to the Lewis acid's strong electron withdrawing ability. And the second way was just increase the temperature of the overall reaction vessel, because by increasing the temperature, you're able to better protonate this double bond. Let's see, double bond here that you can see when the carbonyl kicks back down. But there was only discussion on that being possible with carbonyls rather than maybe something like a basic alkane. So really, I found interesting that there was not many changes present in the spectroscopy, rather just that you start with 2 reactants and you end with a final product, because they both have the same number of double bonds. Each reactant has a single double bond, where the product has 1 overall double bond. But it can vary based on the reactants with your hydrogen NMR, because basically you can form like a cyclical shape, meaning that the septet, or not, it's a septet, you can form like a septet based off the alkene's presence next to the double bond. So I hope you enjoyed my little presentation, and thank you for a great semester.